So a couple of years ago, when I was in Poland, I gave a talk about towards a living world. Um, and the idea was to give a computational account of, um, some of what is entailed by biological agency. And what I settled on were two properties, metabolism and reproduction. And I gave a sort of a toy Rolang model of that. And then I pointed out that with those two properties, you got something that looked remarkably like the core of a Casper validator. And sort of walk through the correspondences. And the interesting point is that we didn't have there wasn't a goal to model Casper, right? There was a goal to model biological agency. And then I made a few points which had to do with when we're modeling things like when we're working with certain abstractions like physics, there's no life in physics. Life ends up being an emergent property from the physical perspective, or at least in modern physics. And the idea that somehow the living world is that the physical world is barren of life is I think at the heart of much of, or sorry, not the physical world, but the physical principles are barren of life, is a kind of conceptual mistake. And I wanted to argue that if you get it, the principles right, then life shows up much earlier in the stack, so to speak. Now, I recently stumbled across a talk that Eric Smith gave at the Santa Fe Institute. And in his and there's a book associated with the talk, and it's called the Origin and Nature of Life on Earth. Now I can't. I mean, his talk was like a good. It was over an hour long, and so I'm not going to do justice to that, but I will give a kind of cartoon summary, and essentially, his argument is that geochemistry driven to states that are far from equilibrium, because of A, the sun, and B, the planetary formation, will eventually produce life, right? So that you get it's not accidental. So despite Francis Crick's comments to the contrary, and other scientists' comments to the contrary about the unlikely nature of life, they Eric Smith and his co-author argue that in fact life is much more inevitable, and he argues that we have to view life from a whole systems perspective. So he looks at it as the fourth geosphere. So you have the lithosphere, the hydrosphere, the atmosphere, and the biosphere, and that shifting the perspective from individual living organisms to the entire biosphere is the right perspective, and uh, and as a one articulation of the one refinement of this kind of cartoon characterization of Smith's argument is that at a minimum, what you get in this sort of march towards life from geochemistry that is far from equilibrium is uh, uh, metabolic processes. And one of the points that he observes is that metabolic processes are remarkably the same in all living organisms. That there's this core process that is the same across all life on Earth. And I was really shocked. I hadn't realized that metabolism was effectively the same. And because I had really from first principles reasoned towards reasoned that metabolism and replication were two essential properties of life. And this really had to do with how do you give computation a form of agency that will ultimately slot it into a natural selection process. And metabolism and replication are two of those properties that seem essential ultimately to fit into a natural selection style agency. Now, one of the things that's really remarkable to me, though, is that differentiates the computational perspective from the biospheric perspective is that if you can give a completely computational account of something like metabolism, then and there's a reason why one might think it is possible to do that, which I'll get to in a minute. But if you could do that, then you can lift Smith's argument from geochemistry, right? So there's something valuable and important about the perspective of the sort of situated perspective that he's taking, which is it's very practical. It relies on an evidentiary chain that comes from whatever we can gather from the record and the left behind on Earth by life, and things of that nature. So it makes for good science, and the perspective is sane and rational in the sense that at least all the life that is heterotrophic, meaning depends on other life for for metabolic sustenance. That's all interconnected, right? It's a giant dependency graph that pretty much spans the entire biosphere. I mean, there are some autotrophic life forms, I guess, but by and large, what you're looking at is a giant dependency graph that makes life, sort of into one big bundle. So there's a good reason for thinking about it, in situ. But the extent to which you can lift it from the situation to a computational account is the extent to which you can use bisimilarity to gaze out into other contexts and other situations, physical situations, and observe the processes which might be which we might also consider either metabolic or living. So for example, who's to say that with the right lens, we don't find things that we call living processes in a star, or the chemistry of a star. I mean, maybe it's not there, but the fact is we can kind of use biosimulation as like a microscope or a telescope, right? You can think of it as sort of like X-rays, in the sense that we can gaze out, in the same way that we couldn't see through the skin of living creatures, of vertebrates, for example, prior to being able to take images using X-rays. Similarly here, biosimulation allows you to sort of see through or into the nature of processes, and thus notice when things are the same somehow, and and that would allow us to look for life outside of the kinds of contexts and situations that we had originally suspected life might be. So in particular, one of the places that I have for well over a decade suspected that we might find life, and I'm sure this gets me labeled as a nutcase, but if you look at all the different proposals for quantum gravity, one of the things that stands out is that it forces the space-time itself to be computationally complete. In the same way that we can build a universal quantum computer. Well, if you marry space-time and quantum mechanics together in a successful way, then space-time itself becomes something where you can host a universal computer. And once you can host a universal computer, then it becomes at least possible in principle. I'm not saying that we have evidence thereof, but it is possible in principle to now build processes that have the complexity or the arrangements by similar to metabolism and replication and other properties that we might reasonably associate with life. And so in this sense, one can think of the actual fabric of space-time as something that is potentially alive. And what this does is it puts a kind of quantitative, predictive framework around proposals that Christopher Alexander makes in The Nature of Order. So he argues that life is a property of space. If you read his work, he's arguing that this is objective, and while his statement is qualitative, it is not intended to be solely metaphorical. It's not a whimsical statement by a world-class architect. It's clear that he's attempting to bring mathematical tools to the idea in such a way as to make it clear, but he never crosses the line where it goes from a qualitative statement to a quantitative one, in the sense that one can calculate and see that, in fact, there is a kind of biosphere that is associated with space itself. But here we're talking about we're talking about a set of tools that are unique to the computational perspective, that allow us to look into the physical world and ask questions, and test the ideas of someone like Christopher Alexander. So let me stop there and see if this is making sense.
Yeah, this is like completely mind blowing.
Cool.
Yeah,
Yeah,
I'm following
yeah.
the general train of thought.
Cool.
So this means that maybe we have some very large life forms in the universe. And we cannot see it right now because
That's right.
like,
Exactly.
yeah.
Right. Yeah. And it's kind of a natural thing to, it's a natural progression, in the sense that, Smith is saying, stop looking at individual organisms as the only way to investigate life, and look at the biosphere, and look at it from, these various angles that he's proposing. So one of the tools that he looks at is phase transitions, in regimes that are far from equilibrium. And he applies notions of stability and error correction in this setting. And so, he has a very interesting story to tell, but the point is that he's kind of widened the perspective. And I think that you can actually widen the perspective further. So let me return to what a comment that I made at the beginning. If you stare at the periodic table from the perspective of a computer scientist, what it looks like is a big rewrite system, right? You've got a bunch of computational agents, all of the elements, and the elements have internal structure, i.e., their nuclear structure, that gives rise to a host of rewrite rules. For example, sodium and chlorine interact with each other through electron, sharing or exchange, and you get salt, right? So Na plus Cl rewrites to salt. So from a computational I mean, one of the big insights in the last 20 years was the work of Ehudi Shapiro, and picked up by many others, Luca Cardelli, Regev Aviv, and many others, who showed that with a stochastic version of the pi calculus, you can faithfully model chemical, biochemical, and biological interaction. And so this idea that it's the geochemistry in far from equilibrium states that gives rise to life. Well, I mean, when you lay that side by side with the work of Shapiro and others, you begin to see, well, it's not actually so far-fetched that you could model the chemistry, and hence the biochemistry, in this way, and begin to get an account of a computational view of what is life. So that's that gives us a little bit more to hang our hat on, so to speak. And then the other thing that is interesting and goes to comments I was making before I pressed the record button. So I was recently talking with a friend of mine. He's a musician friend who sort of left his career in general relativity because physics has been moribund since the 1980s. Um, it just hasn't changed. There haven't been real exciting advances, at least from his perspective. And I think Lee Smolin and other very reputable physicists make a similar claim. So anyway, I was describing to him the research program of discrete differential geometry, which I've only just discovered. And he was making a comment that was very similar to the one I was observing, which is, well, this is very intuitive, and it looks like the sort of thing that you would write down if you wanted to do a kind of intuitive quantum gravity. And I agreed with him that it had it had that kind of promise, that it looked like one could do something along those lines. There's a lot of work to be done. But what I pointed out that he wasn't aware of, because he doesn't study computation, is that using the same kind of methods that I used in modeling the Fano plane, you can easily turn the kind of wire meshes that they use in discrete differential geometry into process models. So there's an algorithm or a functor which will take you from the world of discrete differential geometry to the world of the process calculi. But then once you've expressed, and one of the points I make in the model of the Fano plane is that the Fano plane, you have some interesting choices. You can sort of have the Fano plane just kind of just flash into existence for a moment, and then the process evolves, and you can no longer find the Fano plane structure. Or you can make it stable because you recurse in you have the structure be recursive, so you revisit the same state over and over again. And I use the same trick in the zero knowledge, the ZKP work that I was talking about when I modeled the graphs, the three colorable graphs. So this same idea where the process keeps evolving, and every time it revisits the state, which can be shown to be isomorphic to the graph. But you can relax that property so that it doesn't get back to the original state. And what happens then is that the graph or the wire mesh starts to evolve in time. And this is at the heart of what's going on, or how do I say this? This is an analog of the kind of thing that goes on in general relativity. So now you think of the wire mesh as a quantum space-time, and then to fulfill the intuitions of Einstein's equations, that space-time has to change in response. So in particular, the metric tensor is going to have to change. What is close to what will change as a result of the stress energy tensor. Right, so the stress energy tensor is telling us how matter and energy is distributed throughout this wire mesh. And as a result of the matter and energy, this space-time is going to reconfigure itself, because there's this kind of mutual recursion between the stress energy tensor and the metric tensor. But you have the capability to change the mesh smoothly and nicely, because if you have expressed it as a row calculus process. So you can arrange it so that the evolution of the process aligns with the directives of the stress energy tensor, which then informs the metric tensor, so that will shift where the matter and energy is located. And then you can, which will then, you know, again change the metric tensor, right? So you get this recursive loop happening, but you can write it down. At least potentially you can write it down. And this was the insight that I had ages and ages ago, was that there seemed to be there seemed to be a path to beginning to realize the quantum gravity stuff in this setting. But at the time, I didn't have the tools of discrete differential geometry. And now that I have them, there is this research program seems a lot more solid, or at least it's more likely that that we have all the pieces that you need to put together in order to do this. And just to test and see if there are bugaboos in the mathematics, or if you can do it. Now, one complication is that these are not just wire meshes, right? They're complexes. So you have boundaries like surfaces or triangles, not just vertices and edges. And potentially you can do this at any dimension. And I would argue that you use the annihilation version of the row calculus to lift it, to handle to get versions of the approach I used in the Fano plane to model complexes. But I haven't done those calculations, so it's right now it's just an intuition. But that so now to put it all together, I'm arguing. Initially I argued that there will be enough structure in quantum gravity to have a universal computer, and as a result, we could look for life like actually in space-time itself, as well as in configurations of matter and energy, and that this view is facilitated by a computational account of biological agency. And then I took another step in refining this perspective, analyzing some of, in a very small new level of detail, the perspective that Eric Smith and his colleagues get from life as effectively geochemistry far from equilibrium, and observe that in fact computational models of chemistry of that kind are feasible using stochastic versions of the mobile process calculi, and that and then taking another step to suggest that there is at least a path worth investigating, where you take process models of discrete differential geometry to give computational analogs of general relativity, and and as a result, now you can analyze the resulting models using biosimulation and look inside those models for arrangements that are biosimilar to processes that enjoy metabolic and reproductive agency. So let me just check in. Does that make sense?
Yeah, I think I can follow. And I would like to ask you, from that perspective, what does it mean to have enough structure? I mean, can we look at the weather and on Earth and the climate and some kind of living organism?
It is certainly possible. Yes, I mean it's very. It seems to me unlikely that you have, like let's say you look at a hurricane system. I think you have notions of stability, but I don't think you have notions of metabolism and reproduction. Like so.
I mean, this is what. Yeah, I wanted to ask you, what exactly do you mean by life? You're
Right.
not. You don't mean like conscious life in like, right? Doesn't have to be, right?
I didn't say anything about consciousness. I'm starting from bits and pieces that I can point to, right? So I can point to metabolism, and I can give fairly convincing analogs, right? At least convincing enough that it's worthwhile for more people to take a look. And we can make this very precise, right? So to the extent to which we find, the Krebs cycle, showing up in some form across all organisms, and that's just chemistry, and we can model all that chemistry with stochastic process calculi. That's totally reasonable, right? And then we can go beyond that, so we can look at not just reproduction, but we can look at reproduction and the transmission of genetic information, and all of that is absolutely reasonably modeled in the process algebraic setting, right? So these two basic aspects of life, metabolic and reproductive agency with the transmission of genetic information, that much we can certainly model. Now, is that life? I think there's a lot of debate there, but the point is that what we're showing is a methodology. Show me a property of life that you can calculate with, right? And then I'll show you a method to translate it over into this other setting, and that this other setting has lots and lots going for it, which is why you want to use that setting, right? Instead of using differential equations, let's use a formalism that's compositional.
Yeah.
As an example, right? Instead of using differential equations, let's use a formalism where we have a notion of bisimulation. Let's use a notion where we have let's use a formalism that has a notion of substitutability. Let's use a formalism that has a notion of types and classification. So all of these things are going for you in the mobile process setting that makes it so it's not just that it's feasible to move your calculations over into this domain, but that if you do, you get all these other advantages, right? That's kind of the point.
So this means that life doesn't have to be with DNA, for example. I mean,
doesn't have to be with it, right? So the argument is once you have once you have a computational account, there's no reason why we can't find silicon-based life, and I don't mean silicon in the sense of computers, wires and and bits, but rather, you know, that the chemistry that is supporting the metabolic, reproductive, and other biological agency is based in silicon.
I mean, the question is, for example, I can ask, is my arm alive?
Yes.
Like, it's, if someone is looking just my arm, is it alive? It's difficult to say, right?
You can ask those kinds of questions, and I think that you know, the computational answers would ultimately bear out a lot of our intuitions. By itself, the arm is not alive, right? If you excise the arm from its context in the body, it quickly dies. And it ceases to have the properties that we associate with life. For example, metabolic agency.
Or I was thinking, if someone if someone can only see my arm, it will have a different perspective. So this is how I'm like understanding what you're saying.
Yeah, it will observe that the arm is somehow connected to a larger system that is right. You know, and that then goes back to Smith's point about looking at the biosphere, right? Because heterotrophic, well, all of life, including the autotrophs, seem to be interconnected, right? Everything eats everything else.
I mean, the sun is also like it's you know,
yeah, well,
it's
yeah,
fuel and
yeah, that's right, exactly. So anyway, I mean, to me, this kind of research program has been just fascinating for a number of different reasons. You know, in particular, I think it says, you know, how do I say this? We've started to see that quantum mechanics, that the computational perspective that that was brought to quantum mechanics has begun to change the you know, the dialogue about physics. And this was something I predicted 20 years ago, that you know, you know, in a kind of cartoon way, computation used to be kind of the water boy for science. You know, go and calculate this for me. I'm busy doing science, and I'm too busy to do these calculations. You know, you computer, go and do these calculations for me, right? But that's going to change. In particular, computation as a perspective on, you know, how on mathematical reasoning and general reasoning about physical processes, it's going to flip around, and computation is going to change the way we do science. And this is already happening. So as an example, Chiara Marletto and David Deutsch have proposed a different framework for doing physics. So instead of expressing dynamical laws and initial conditions, so laws of motion together with initial conditions, they propose that physical theories be expressed in terms of counterfactuals. So what transformations are possible and what transformations are not possible. And they make this proposition precisely because under the dynamical laws and initial conditions formulation, it's very difficult to give an exact formulation of information. Information seems to be, you know, somehow only an emergent property and therefore not fundamental. Life is also an emergent property and not fundamental. You know, their argument is that if you shift the physics away from dynamical laws and initial conditions to formulations in terms of counterfactuals, then you can account for important phenomena that are properly the domain of physics, such as information. So already we're seeing the shift in science towards imposed by and sorry, so just to complete the argument, and a lot of what they said was not just because of the advent of computers, but the real impact that quantum computation has had on physics. Right. So if there hadn't been quantum computation, it might have easily and the impact that it is having on practicing physicists like Bob Cook, there would have been less likely this kind of proposal from Deutsch and Marletto. And my argument is that this is only just the beginning. That computation is going to, over the next 200 years, computation is going to fundamentally revise all of the physical sciences because of compositionality, because of bisimulation, and so on. And so the proposals that I've talked about today have to do with exactly that, right? They allow us to change the way we view the world. So a world that is based on dynamical laws and initial conditions, that perspective on the world is devoid of life. And if you grow generations and generations of humans thinking that life is not fundamental, then that might have an impact on how they view the world. Right? So if you have centuries of humans thinking that life is not fundamental, that might subtly influence the kind of world they bring about. A world which is rapidly moving towards towards this, the sixth mass extinction. That might have a play there. But if computation can show us, no, life is fundamental, then I think it is possible, at least in principle, to move towards a different relationship to the living world so that we're not rushing headlong towards mass extinction. So with that, that's where I'll kind of tie things up.
We'll be nominating you for a Nobel Prize someday in the future. Right?
And I doubt it very much.
Yeah.
And to me, it's not. The big prize would be if we can just build a coordination system and people use it so that we don't throw all of human culture out with the bathwater as the shit hits the fan. That would be
Yes.
an amazing prize.
Agreed.
Thank you so much. I'll see many of you.
I had one thought. You mentioned UFOs in one of the climate talks the other day, and the government is coming out with a lot of new videos of UFOs. And you just mentioned life existing within space-time itself. There's been a theory that UFOs may be living organisms. There was a guy named Trevor James Constable. I mean, he was he's kind of in the esoteric and the occult, but he's always maintained that most UFOs, most UFOs that we really couldn't identify and had some other substance to them were probably living organisms. And he's got one book called The Cosmic Pulse of Life and another one called They Live in the Sky. But anyway, I thought I would throw that in because there's two connections there that I'm sort of showing my roots now in the UFO field. I used to research that field quite a bit.
Oh, interesting. That's very interesting. Yeah, I mean, who knows if they're extra, if the phenomena that the armed forces are reporting are extraterrestrial at all. I mean, just because they're they're unidentified aerial phenomena doesn't mean that they come off planet. They might in fact be they might in fact be terrestrial, or as you say, they might be organisms that are just using what's available in space-time, but in a way that we hadn't thought about before.
Yeah, exactly. Great talk. Thank you, Greg.
Oh, thank you guys. I'll see many of you in stand up in about 10 minutes.
Thanks. Bye bye.
Ciao.